In this video, we'll explore the summing amplifier, which can be constructed in both the inverting and non-inverting form. If you look at our basic inverting and non-inverting amplifiers, we apply a single input, either to the inverting or the non-inverting terminal respectively. What will happen if instead of a single input, we apply multiple inputs at either end of the op-amp? Let's try to answer this question. First, consider the case of inputs at the inverting terminal of the op-amp. Suppose we have three inputs VA, VB and VC connected to the inverting terminal of the op-amp via three resistors, RA, RB and RC respectively. We'll call the inverting terminal as X. As the op-amp is in negative feedback, we have the virtual ground condition. Hence, Vx is equal to 0. Suppose the currents through RA, RB and RC are IA, IB and IC respectively, and the current through RF, the feedback resistor, is IF. As no current flows through the input terminals of the op-amp, IA, IB and IC will add up at node X and flow through RF as IF. Hence, we have IA plus IB plus IC is equal to IF. Using Ohm's law, we get VA minus Vx upon RA, plus VB minus Vx upon RB, plus VC minus Vx upon RC, is equal to Vx minus Vout upon RF. As we found out before, Vx is equal to 0. A little manipulation gives us, Vout is equal to minus RF upon RA into VA, plus RF upon RB into VB, plus RF upon RC into VC. Thus, this circuit gives a weighted sum of the inputs applied, in an inverted form. Hence we can use this circuit for scaling operations. The scaling operation has a lot of different applications. This is quite useful in the music industry, where the producer might want different instruments at different sound levels while mixing a song. Suppose we choose the same values for all resistors, that is, RA equal to RB is equal to RC is equal to RF. If we substitute this in our previous equation, we get Vout is equal to minus of VA, plus VB, plus VC. In this manner, we can get direct addition of signals as well. We can also execute averaging operations using this circuit. If we choose RA is equal to RB, is equal to RC, is equal to 3RF, we get Vout is equal to VA, plus VB, plus VC upon 3, which is the average value of the three input signals. These concepts can be extended in general for N resistors, for which we get a similar equation. Now let's turn our attention to what happens if we apply the inputs VA, VB and VC to the non-inverting input. Let's call the voltage at the non-inverting terminal Vx. We can find the value of Vx in terms of VA, VB, and VC easily by using the superposition principle. The superposition theorem states that a circuit can be analyzed with only one source of power at a time, and if we add the corresponding component voltages and currents algebraically, then we get what they'll do with all power sources in effect. So, we will keep an input VA, or VB, or VC, on, one at a time and see the effect on Vx. We'll replace VB and VC by ground nodes. Thus, resistors RB and RC appear in parallel and form a resistor divider circuit with RA. Hence, Vx will be RB, parallel RC, upon RA, plus RB parallel RC into VA, by simple voltage division. Similarly, we can find the contributions of VB and VC. Due to symmetry, we can write their values directly. By adding the contributions of VA, VB and VC, we get the actual value of Vx. Now that we've found the value of Vx, the circuit boils down to a non-inverting amplifier with a voltage input of Vx. Hence, the value of the output will be 1 plus R2 by R1 into Vx. Substituting the value of Vx found previously, we get the following equation. Note that the output is not inverted in this case, as expected. The gain may seem a bit complicated, but if we choose the same values for resistors RA, RB, and RC, Vx reduces to VA, plus VB, plus Vc by 3, thus giving us the average value of the three inputs. Further, if we choose R2 by R1 as 2, we get Vout equal to Va, plus Vb, plus Vc, the sum of the three inputs. Similar to the inverting case, this concept can be extended for n inputs. Not only is the summing amplifier a very useful circuit, the methods used to find its gain captures all the techniques required to solve any op-amp circuit which contains multiple resistors and op-amps, which is why you should get really comfortable with the concepts taught in this video. If you have any doubts, feel free to ask in the comments section. Don't forget to like, share and subscribe.